Okay guys, so we're looking at lab 13 here, and lab 13 is about binary, right? How do we take the zeros and ones and convert them into something we can use and the computer can use, and how does the computer interpret what we're doing? We're going to look at three different ways that the computer might interpret some binary stuff, and I'll work you through it, and then you'll have a worksheet tomorrow to answer some of the same kinds of questions. So 32-bit 2's complement integer coding sounds really complicated, but signed integers are typically stored in 32 bits. Okay, so you get a big string of 32 bits like this. 4 consecutive bytes, so a byte is 8 bits. In 2's complement form, and the leftmost bit is the 1. Okay, if there's a 1 here, then it's negative. 0 is represented by all zeros, and all other 32-bit combinations start with 0. Represent positive integers. The 2's complement representation for positive integer is just its binary equivalent. So let's talk about a binary equivalent. So the example here is 13. Okay, if you think of the very first spot as 2 to the 0, and then 2 to the 1, and 2 to the second, and 2 to the third, etc., because we're doing binary, okay, you got 1, 1, 0, 1, so there's 1, 2 to the third, 1, 2 to the second, no 2 to the first, and 1, 2 to the 0. So 2 to the third is 8, 2 to the second is 4, 2 to the 0 is 1. So if I take 8 plus 4 plus 1, I get 13, okay? Let me do one more example with you. Let's do it the other way. Okay, so let's take a look at the number 75. Okay, so let's look at how many 2 to the 0, 2 to the 1, 2 to the second, 2 to the third, 2 to the fourth, 2 to the fifth, 2 to the sixth, etc. Okay, so 2 to the sixth is 64. Okay, so I need one of those. Okay, and then if I put a 64 in, the remainder is 11. So 2 to the fifth is 32, I don't need any of those. 2 to the fourth is 16, I don't need any of those. 2 to the third is 8. Well, 8 is smaller than 11, so I'm going to need one of those. And if I take 8 away from 11, I'm left with 3. Well, 2 to the fourth is bigger, so I don't need any of those. 2 to the first is 2, so I am going to need one of those. Okay? And then you're left with a 1. So 1, 0, 0, 1, 0, 1, 1 is the binary equivalent of our decimal 75, okay? And so you're going to be given some numbers like this, and potentially that whole block of numbers could represent an actual number in decimal. And so you might have to do some converting, okay? So if you do have a question with that, please let me know, okay? Another thing that could be used here is we could be trying to send a message. We could be trying to convert this into characters. Okay? So what may happen is you might take this 32-bit string here and take them in chunks of 4 and look at the hexadecimal equivalents. And then look at an ASCII code and convert it. If you guys have ever seen the movie The Martian, at one point when he finds the Mars rover and he starts pointing the camera in directions, he realizes that the 26 letters in the alphabet plus some punctuation, if you take 360 degrees and you divide it by, say, 30, that only leaves you 12 degrees, and he didn't think that was enough. So instead, he went to hexadecimal, which is 16, which gives you a lot more leeway, and we're going to show you how this works. So you typically, it says start on the right-hand side. Actually, here we're going to be starting on the left-hand side. That's I think, a mistake in the way it's written here. Okay, so we're going to start on the left-hand side, and then we're going to look at 4 blocks at a time. So 0, 1, 0, 0. So I'm going to find that. 0, 1, 0, 0 is right here, so a 4. And you can see he's placed a 4 here. Okay, the next 4 is 0, 0, 1, 0. 0, 0, 1, 0 is a 2, so 4, 2. Okay, and then 0, 1, 1, 0 is a 6, and 0, 1, 0, 1 is a 5, so 6, 5, etc. And we're just plugging these out of here. I think there is one mistake in here. one of them, like this one is, these two are exactly the same and they're not both 6D. This one's supposed to be 6-9, which means instead of 1101, that should be 1001. Other than that, everything's right. So now you've got these hexadecimal numbers. And you're like, well, what do I do with 4265, 6D, 69, 64, etc.? Okay. Well, on this, and I've attached this on your assignment, you have a link to an ASCII table, okay? And I've got these numbers written down, and we'll go through and we'll look and see what it does. So we go to the ASCII table, okay? We click on ASCII, and I'm just gonna move this up so we can see it a little bit better. And this is what your ASCII table looks like. Now you'll notice there's a column for decimal, hexadecimal, octadecimal. We're going to look at the hexadecimal column in ASCII, okay? And I'm going to write our code across the top here. So we had 4-2, and then 6-5, 6D. Well, you know what? I'm gonna write it somewhere where we don't have to overlap here. So 4-2. 6-5, 6D, 6-9, 6-4, 6A, and 6-9. Okay. So that being said, we have to go to our chart and we have to find these. So 4-2 hexadecimal, okay? 4-2 is a capital B. Okay? 6-5 is a lowercase e. Okay? 6D is an M. 6-9 is an I. Okay? There's another 6-9 here, so I'm going to put that I in there. 6-4 is a D. And 6A is a J. Okay? So I think you can see that if we take that 32-bit string, it could represent a message. If you bring that into ASCII, it spells out the word Bemidji. Okay? So that particular block of code gave us a message. Okay? And that could be one way that the computer interprets this. There's one additional thing that could happen. Okay? So, it could be representing colors. So colors, as you go through this, you're going to get 3 strings of 8 bits, okay? And the first 8 bits is going to represent red, or the amount of red that's in there. The next 8 bits is going to be green, and then the next 8 bits is going to be blue. So RGB, red, green, blue. And you have 256 different possible intensities for each of these, 2 to the 8. And so there's a lot of different colors that could come up. And so what we do is we go back to our ASCII table again, and we say, okay, 0110 is a 6, all ones is an F, 0010 is a 2, 1001 is a 9, all ones are Fs again, okay? So 6F29FF, what color does that mean? Well, there's 2 ways of interpreting this, okay? One is to give an actual color that you might see in the Crayola 64 pack. Well, the only way to do that is to really actually put it into an actual web page, and I'll show you how to do this in a little bit. The other is to think of it more analytically and just say, okay, this is supposed to be red. 6F is kind of in the middle, so a medium amount of red. 29 is a smaller number in hexadecimal, so a small amount of green. FF is the maximum amount of blue. So a ton of blue with a medium amount of red and a little green is going to be some sort of purple, right? So we don't know which purple, but we could say medium amount of red, a little bit of green, and a lot, the maximum amount of blue. So we could describe it that way, which I will ask you to do on the homework. And then let's see what color it is. So if you go to this web page, you have a place where you can enter the color here. So let's do that. Okay, let's see if my whiteboard cooperates here. There we go. So we had 6F, followed by 29, followed by FF. Okay, so you put it in there just the way that you interpreted it from the hexadecimal. You push the button, and boom, just like we thought it would be purple. Okay, and so then you could, you could say, well, is that eggplant? You could give it a name if you wanted to, but that's kind of what we're looking at from that one. Okay, so going back to here, this is the assignment. There's a document. You can either click on the link, or I've shared the document on Google Classroom as well. And it's going to ask you a bunch of questions. What would this look like in binary? What would this look like as a message in hexadecimal? What would it look like as a color? Could you describe it to me? That kind of thing. So that's what I'm looking for in this this lab. So if you have questions, please ask. Okay. Thank you.